Thank you so much for the invitation. So I'm already having a good time and we haven't started yet. So you see the title, this is joint work with Jesse Thorner. Actually, we did this 2 years ago, but the paper just got accepted not so long ago, so it will appear in CREL. And I decided to start the talk with a surprise and end the talk with a surprise. So there will be two surprises. And I had no time to prepare the slide for the first surprise. So the surprise is, I'm revealing it orally now. It's my birthday. Today is my birthday. And that's so cool. So I think like the best way to celebrate birthday, to give a talk, math talk. Yeah, I did that when I turned 40, but that was a long time ago. And in fact, there are other mathematicians with his birthday that I know of. So foremost, there is Alfred Rényi. So he was born on March 20. And then there is Mertens. There is Epstein. There is Ken Ono, March 20. And there is also the Fields medalist Novikov that I know. Of course, not everybody was born on March 20. For example, yesterday, March 19, Bruce Willis turned 70. And tomorrow, Johann Sebastian Bach will turn 340. Okay, so that's the start. And then we start the talk proper. So this talk is for a wider, more diverse audience that I'm used to. So I tried to make the beginning more introductory. Hope you will find this more entertaining than boring. So the story of zero-free regions of L-functions, I think, starts with observations or discoveries by Dirichlet, 1837, and Riemann, 1859, that the logarithm of a Dirichlet L-function is supported on prime powers. So that logarithm can be used to study the distribution of primes up to a given height, and also in various residue classes. Now, one can define the logarithm of an L-function, Dirichlet L-function Ls psi. There's a reason I'm using the symbol psi, not the more familiar chi. That will be clear later. So one can define log of Ls psi as a holomorphic function in any simply connected region where the L function is non-vanishing. Also, I'm avoiding the possible Paulette S equals 1, but that should be obvious. But the derivative of this function, that is the logarithmic derivative of the Dirichlet L function, is more pleasant to work with. And if you write out the logarithmic derivative with the minus sign, so it is given in the half plane, real part that's bigger than 1, as an absolutely convergent Dirichlet series. So the reason is that the L function itself is given in that half plane by an absolute convergent Euler product. And then when you take the logarithm, then this Euler product becomes a sum supported on prime powers, and that keeps being the case after differentiation. So the coefficients are given by the product of the Dirichlet character in question and the von Mangold function. So the von Mangold function, very important object for analytic number theorists, is supported on prime powers. So for a power of a prime p, the value of the von Mangold function is log p. Otherwise, it is 0. And the generalized Riemann hypothesis tells us that we have non-vanishing of the L function as long as we are to the right of 1/2, abscissa 1/2, but that is very much out of reach at present, so we cannot prove this hypothesis. So we come up with narrower zero-free regions where we can define this logarithm or the logarithmic derivative and apply techniques of contour integration, Cauchy's theorem, Mellin transform, etc., to count the number of primes up to given height and in various residue classes. Now, a few decades after these heroes, Dirichlet and Riemann, other great mathematicians stepped forward, like Adamar, end of 19th century, and Delavallee-Poussin, who independently proved the prime number theorem, following the ideas of Riemann principally. And then Gromwall, Landau, Titchmarsh, Page, Siegel have refined their ideas. And this led to the following zero-free region of Dirichlet L-functions and more. So here I try often, you will see, because the subject is so vast and my time is so limited, I try to collect several results in one boxed theorem. And when I don't give attribution, that's because there are many people behind it, and I try to indicate, like here in red, the key players in the story. So there exists a positive constant C1 with the following property. Whenever psi is a primitive Dirichlet character mod Q, then the Dirichlet L-function LS psi admits a standard zero-free region, meaning that in the region defined by the inequality real part of S is at least 1 minus C1 over log of what we call essentially the analytic conductor Q times the imaginary part of S plus 3. There can be at most 1 0. So this is almost like a zero-free region, but there is one mischievous zero that we cannot exclude. If that exceptional zero, also called Landau-Siegel zero, exists, then provably psi is quadratic and non-trivial. In this case, and this is Siegel's famous theorem, very relevant for my talk, for all epsilon, all positive epsilons, we can, so now we can focus on quadratic psi and the real axis, and we can bound away this possible exceptional zero ineffectively from one. More precisely, there exists a constant C2 that depends on epsilon, but in an ineffective manner, meaning that we don't know a way to write this down as a concrete function of epsilon. We just know this C2 exists such that as psi is running through quadratic characters and Q is the conductor, then L sigma psi is non-vanishing for sigma to the right of 1 minus C2 Q to the minus epsilon. So as opposed to the standard zero-free region where we bound away the zeros by constant over log Q, here we bound away the zero, this one possible zero, by a constant times Q to the minus epsilon. And in fact, this theorem comes with lower bounds, so it's not just non-vanishing that is happening, but we can bound these objects from below in absolute value. But this I omit for simplicity. Now, from this theorem, let me weaken this theorem and extract a convenient bound, at least for the purpose of this talk, especially, so this is the bound I want to extract, giving credit to De La Vallée-Poussin and Siegel and maybe all the other people. So for all positive epsilon, so this is a weakening. It's a consequence of what I displayed before. There exists an ineffective constant, let's call it C3, such that for all primitive Dirichlet characters psi mod Q, L sigma plus IT at psi in absolute value is bounded away by that constant times the analytic conductor Q plus theta minus epsilon, as long as sigma is to the right of 1 minus C3 Q plus T to the minus epsilon. So here I do display the lower bound. It follows from the previous theorem when also the lower bounds that I omitted are thrown in. So this result, first, it's simpler to state. It's ineffective, but it's easy to state and understand. And this is especially important for me because this is the kind of estimate I'd like to generalize to all GL1 twists of GLM cross GLN L-functions. So Rankin Selberg L-functions. And one important consequence, so it turns out that the bound I displayed, this weakening of the previous theorem, actually is sufficiently strong to derive the celebrated Siegel-Wallfisch theorem published by Wallfisch shortly after Siegel's paper, which says that as long as the modulus of the residue classes in which we want to count prime numbers goes up to any but fixed power of log x, we have equidistribution with a goodish error term. So if we sum up the von Mangold function up to x in the residue class A mod q, then the expected main term is x over phi q. In fact, for q equals 1, we get the prime number theorem in one of the early forms, in goodish analytic form. In that case, the asymptotic would be x. And if you believe, I mean, we expect that prime numbers are equidistributed in reduced residue classes, x over phi q should be the main term, and then there is an error term with a constant depending only on this a, the exponent of log x in this theorem, the error term being x over log x to the a. By the way, this condition that q is at most log x to the a can be omitted because if q is larger than a large log x to the a, or maybe log x to the a plus 1, I don't know, then the result is just trivial. So what's it's really meaningful in this range. So that's the famous Siegel theorem. And in fact, I will present a generalization of that as a result of our generalization with Jesse of this lower bound for the L function. Okay, so now at this point, I should give a crash course, but it's impossible on automorphic forms, automorphic L functions, Rankin Selberg L-functions. But still, I make an attempt to give you a bit of an overview. So if you understand these things, then cool. Otherwise, you will just pick up some vocabulary and you will feel what's going on. So by this Gothic Fn, I will denote the so-called set of unitary cuspidal automorphic representations of GLN over Q. It would be impossible to define what these are exactly, but say so we'll look at this set when n equals 1, then it's rather concrete, and for n equals 2, we get the classical holomorphic cusp forms or automorphic representations coming from them and the upper half plane, and also the mass forms, the real analytic mass forms. And by the way, everything I'm going to say works over every number field, but for convenience and for comprehension, I will restrict my attention to the rational field. And every cuspidal automorphic representation comes with a central character, which is operant an element of F1, and unitary means, or it's a Hecke character, and unitary means that this Hecke character is unitary. It maps into the unit circle, not some other part of C star. And often it is convenient, and most of the time it's done, that these cuspidal automorphic representations are normalized. So Fn star is the set of normalized representations where normalized means that the central character is assumed to be trivial and the positive reals embedded in the ideal group. So in fact, this normalization is so standard that many authors just forget emphasizing it, and then they secretly assume that they already talk about this normalization. So the advantage is that the associated L function is also normalized. For example, for Rankin Selberg L-functions that we are looking at, if they come from the normalized objects, then the pole, if there is a pole, can only occur at s equals 1, not somewhere else on the real line, real part s equals 1/2. Anyways, each unitary cuspidal automorphic representation of GLN over Q comes with a standard L function, which can be defined as an absolutely convergent Euler product. At each prime, we have an Euler factor that's 1 over a polynomial of p to the minus s, which is of degree at most n. And it happens only at finitely many primes that this degree is strictly less than n. For example, a Dirichlet L-function satisfies this template, then n equals 1, and we have 1 over 1 minus chi p to the minus s in the denominator, and this chi p vanishes if and only if pi divides the modulus of the character. In fact, here I'm restricting to primitive characters, so when p divides the conductor. So for all but finitely many primes, these parameters alpha j pi p are non-zero, yielding an Euler factor of degree n in the denominator. Those are the typical primes, the unramified primes. Of course, here we should explain what these roots alpha j pi p are, the so-called Langlands or Sateki parameters. At any rate, if you multiply out these denominator expressions yielding a polynomial in p to the minus s, then the coefficients of this polynomial, also called the Hecke polynomial, can be identified in full generality, even at the ramified primes, as certain Hecke eigenvalues of new forms lying in pi. So for the unramified case, there is the important work of Tamagawa and Sataki, and then Kondo Yasuda filled in the picture of what happens exactly at ramified primes in this language. So the point is these alpha j pi p's and the coefficients after factoring, also the symmetric polynomials of the alpha j pi p's, are very concrete quantities that you can extract from the representation. In general, an L-function you can think of as a kind of blueprint or DNA of some global object, in this case, a unitary cuspidal automorphic representation, and the Euler factors can be thought of as various local lenses to look at this global object. Now, as with Dirichlet L-functions, the standard L-function can be completed with n gamma factors, n being the degree of the L-function, and the resulting complete L-function lambda s pi satisfies a similar functional equation as Dirichlet L-functions. In fact, this L-function that you see displayed, at least the look of it, resembles the product of n Dirichlet L-functions. Certainly, a product of n Dirichlet L-functions can be written that way, and it turns out that such a product of n Dirichlet L-functions is the L-function of an automorphic representation, or so-called isobaric automorphic representation of GLN over Q, not of a cuspidal automorphic representation, so not an L-function of a cusp form, but an L-function of an Eisenstein series. And more generally, if you multiply various standard L-functions, that product itself can be understood as an L-function of an isobaric automorphic representation on a larger group. So there is some beautiful things going on here with lots of harmony. But here in this next slide, let me focus on how to understand, how to think of F1. So cuspidal automorphic representations of GL1 over Q. This happens to be an abelian group. That's very important for us. It's a group. It's not just a set, it's a group. Characters form a group because this is actually the set of unitary Hecke characters. So ideal class characters, unitary ideal class characters, so to say. So these are characters mapping from the ideal group into the unit circle such that the character is trivial on the embedded Q star in the ideal class group. And very important for us is that F1, this abelian group of characters, which generalize in a sense Dirichlet characters, and we look at that in a moment, this group acts on Fn in a rather transparent way. So if you pick pi, your GLN cuspidal representation, and you pick a chi, your Hecke character, unitary Hecke character, then assigned to pi and chi, you can assign to pi and chi the cuspidal representation pi tensor chi, which is itself a GLN cuspidal representation, which is given by this very simple formula. You pick G from GLN AQ, AQ is the ideal group, then the determinant is an ideal. You can evaluate chi at this determinant, multiply pi G with it, and that's the representation, the twisted representation. You can twist pi by chi. Any GLN representation can be twisted by a character. And now, very concretely, because we work over Q, a Hecke character, an ideal class character, can be thought of, it corresponds bijectively to a pair of a real number, T, and the primitive Dirichlet character, psi. And here we include the Dirichlet character. So you can think of this group of chi's as this group of pairs, T and psi, and it's very easy to describe the group law in this language. So how do you multiply to a pairs T and psi? The T components need to be added up, and the psi components need to be multiplied more precisely because we want to stick to primitive Dirichlet characters. When you take two psi's, you not simply multiply them, but you take the underlying primitive character that induces the product. And then it's really a group. And under this correspondence, the L function of chi, also called the Hecke L-function, is nothing but a shift of the Dirichlet L-function. So Ls chi, when chi corresponds to the pair T psi, is nothing but Ls plus It psi. So over Q, GL1 L-functions are exactly the same as shifts by purely imaginary numbers of Dirichlet L-functions. And more generally, the effect of twisting by chi that I explained in the previous box corresponds to twisting the representation by the Dirichlet character psi, and then shifting the variable s vertically to s plus it. So we need to, in this talk, we shall use this language. So I'm trying to help you get used to it. So whenever I twist by chi, that's the same as twisting by a certain primitive Dirichlet character and then shifting the variable by it. In particular, shifting s by it is a twist by certain very particular Hecke characters. So we'll adopt this group theoretic language. We'll treat shifts by purely imaginary ITs and shifts by primitive Dirichlet characters at equal footing. That's important for us so that we can do things in the generality I'd like to. Anyways, the results I told you about, classical results by Delavallee-Poussin and Siegel for Dirichlet L-functions have actually been extended to standard L-functions. And here, again, I should give credit to many people, but some important, very important milestones include Gergely Harcos 76, who showed the non-vanishing of standard automorphic L-functions, Moreno, Hofstein, Ramakrishnan, Ivanez Kowalski's, here I mean their book, Analytic Number Theory, which has lots of valuable material and results. Bromley 2019, and more recently, this 402 paper, Jiang, Li, Thorner, and Wang in 2021. And here is, again, a joint theorem of several theorems where I only display non-vanishing. I focus in this theorem on zero-free region of standard L-functions, but equally lower bounds can be added to this result as well, omitted for simplicity. So for each degree n, there is a constant C4, and this is an effective constant actually with the property that whenever pi is a shift normalized Caspidal representation of GLN over Q, then the associated standard automorphic L function, just as with Dirichlet characters, has at most 1, 0, and it's necessarily real and simple in the region resembling the region for zero-free region for Dirichlet L function. And here you see the star here in Fn star is important. Otherwise, I couldn't claim that this exceptional zero is necessarily real. Then it would happen at some other height. So here shift normalization is very convenient. And if that exceptional zero exists, then pi is self-dual. So when you look at the functional equation of LS pi, the functional equation connects LS pi with L1 minus S pi tilde, just like in the functional equation for Dirichlet L-functions, you have to conjugate the characters. So conjugation corresponds to duality in automorphic forms. In fact, the dual L-function dual form has conjugated alpha JP. So it's quite easy to keep track of what it means. Those parameters ought to be real. That's self-duality. Anyways, if pi is self-dual, then there is an analog of Siegel's zero-free region or zero-free line segment or zero or lower bound. So there exists an ineffective constant depending on pi and epsilon, such that L sigma pi twisted by chi is non-vanishing for all quadratic characters chi, as long as sigma is at least 1 minus this ineffective constant times c chi to the minus epsilon. By the way, c pi and c chi is the analytic conductor that I haven't defined to save time. It consists of the usual conductor of the automorphic representation and the shift parameters in the gamma factors in the completed L function or the infinite part of the L function. Anyway, this is just a good measure for various purposes like subconvexity of the L function. How big is the L function? So C pi is there and C chi is down there. Now, the talk is really about Rankin Selberg L-functions. So these are associated to a pair of Caspidal representations. So let's take pi from Fn, rho from Fm, and then Ls pi cross rho has this structure, similar structure as for standard L-functions, but the Euler factor has a polynomial in the denominator that is typically of degree nm, as opposed to just n, because there is also n and m. And if P is an unramified prime both for pi and rho, then in fact, you can arrange these coefficients alpha j k so that they are equal to alpha j coming from pi and times alpha k coming from P. So very simple equation can be given for those parameters when P is unramified for both pi and rho. Now, the L-functions, just as standard L-functions, can be completed with NM gamma factors, and the resulting completed Rankin-Selberg L-function satisfies a similar functional equation as standard L-functions. And also, again, I'm omitting many details, but analytic properties like meromorphic continuation with location of pose, etc., are known for these L-functions. So in many ways, these L-functions behave as standard L-functions of degree Nm. And in fact, the deep Langlands functoriality conjectures state, in particular, they predict that the Rankin-Selberg L-function as above is actually a standard L-function coming from a cuspidal, not necessarily cuspidal, but an automorphic representation of GL and M. An isobaric sum of cuspidal representations of degrees summing up to Mn. Anyways, Hofstein and Ramakrishnan 30 years ago used this hypothesis, this consequence of Langlands functoriality that Rankin-Selberg L-functions are actually standard L-functions, something that we don't know, to prove the non-existence of lambda Siegel zeros other than those of Dirichlet L-functions. So those are very nasty. Those cannot be excluded by this device. So if we knew this hypothesis, then this talk wouldn't be, because this talk is about what can we say about lambda Siegel zeros. Now, about non-vanishing of the L-functions, so the analog of kind of the prime number theorem in weakest form that the L-function is non-vanishing on the one line was proved by Shahidi in 81. And this initial zero-free region has been strengthened in various ways by Moreno, Sarna, Goldfeld, Lee, Humphreys, and Zhang. And here I'd like to collect what I think is the state of the art. So things get more complicated. One big difference between Rankin-Selberg L-functions and standard L-functions, that when you start to form Rankin-Selberg L-functions from Rankin-Selberg products, those are no longer, those L-functions are no longer accessible. So you can start with cuspidal representation and form Rankin-Selberg L-functions, but when you work with the hypothetical Rankin-Selberg product objects, you can no longer form Rankin-Selberg L-functions, and things become much more difficult. So this talk addresses a case, in a sense, more difficult or less accessible than that of standard L-functions. And this is reflected in this theorem. Again, there are many people behind it, which tells us that things don't look so great for Rankin-Selberg L-functions as for standard ones. But of course, we have some important and valuable results. And here is a collection. So there exists an effective constant C6, depending on the degrees, such that whenever pi and rho are shift normalized automorphic forms on GLN and GLM respectively, then LS pi cross rho, Rankin-Selberg L-function, has no zero in this weak region. I call it weak because if you look at the bound for the real part, so we can go slightly to the left of one, so that's better than what Shahidi proved, although that's a fundamental result, but then you want to move to the left of one, that's always the game. So here you can move slightly to the left of one, C6 times analytic conductors raised to minus n minus m, and imaginary part raised to minus nm. So we have a polynomial of the analytic conductor in the denominator, as opposed to a logarithm or just an epsilon factor. So this is basically the best we know. The exponents have been improved a little bit, but the exponents are large, and this is the only effective kind of zero-free region that we have in generality. However, when one of the two guys, pi and rho, one of them is self-dual, or rho is the dual of pi, then we can say more. Then we are in a similar situation, at least for theorems, as we were previously. So the Rankin-Selberg in that case admits a standard zero-free region. So there is this constant, well, for convenience, I called it C6, same thing as before, has at most one zero, necessary real and simple in this region, where real part is at least 1 minus this constant over logarithm of the analytic conductor. And then if the exceptional 0 exists, then either both pi and rho are self-dual, or rho is actually the dual of pi. And now, finally, I can announce the new result, which is not that new after all, 2 years old. So we extended the celebrated lower bound of Siegel to all GL1 twists of general Rankin-Selberg L-functions. So once again, when I say GL1 twist, I really mean twist by an arbitrary unitary ideal class character. So that means also shifts. That means also the T aspect. T aspect is included, and primitive Dirichlet character twists are included. Both of them are captured by GL1 twists. And special cases here were established by Jiang, Thorner, Wang. Actually, that I already mentioned for standard L-functions, and Humphreys, Thorner, that I didn't mention. Anyways, that result is subsumed. Those results are subsumed, what I'm going to state. So take a pair, not shift normalized, anything, no restriction, just unitary Caspillo representations, pi and rho on, GLN and GLM over Q respectively. And then for every positive epsilon, there exists an ineffective constant, much like in Siegel's theorem, but now ineffectivity also includes ineffective dependence on pi and rho, such that no matter how you twist the Rankin-Selberg with chi lying in F1, ideal class character, on sigma, the real axis, the L function is non-vanishing and in fact can be bounded from below by C7 analytic conductor of chi to the minus epsilon, as long as sigma is to the right of 1 minus C7 analytic conductor of chi to the minus epsilon. Now, once again, let me emphasize for the third or fourth time that chi involves the shift aspect. So if you associate to chi this pair of a real number t and the primitive Dirichlet character psi, then really what you see on the left-hand side is the L value at sigma plus it, a value of the rank of the product pi cross rho twisted by psi. So this is not just a non-vanishing result and lower bound on the real axis. It's actually a full zero-free region, in particular for a single, if you choose chi to do the shift, no psi involved, then in particular you can see that L sigma plus it pi cross rho is at least this ineffective constant times t to the minus epsilon, as long as sigma is bigger than 1 minus C7 t to the minus epsilon. This was not known before. Even this special case was not known before. And so the proof relies on the group structure of F1, just like Siegel's proof relied heavily on the group structure of primitive quadratic Dirichlet characters. But here the situation is more complicated for several reasons. For one, we include the T aspect, something that was more accessible for Dirichlet L-functions. And also we have to entertain the idea. I mean, we have to deal with the possibility of poles in the Rankin-Selberg L-function. So one has to be careful. The proof relies on the group structure of F1 nevertheless, and it utilizes, so the basic idea is similar. It utilizes an auxiliary L function with non-negative coefficients that extends, and that's amazing. You will see that the auxiliary L function we are using is actually a common generalization of both the auxiliary L function used in the De Laval-Poussin proof and in the proof of Siegel's proof. So that's something we found surprising in retrospect, because we only observed this in retrospect. Anyways, this new zero-free region allows us to prove an analog of the Siegel-Wolfish theorem for Rankin-Selberg L-functions. So let me not waste too much time on this. So there is a main term, and then with this main term that is explicitly defined here, we can look at the Dirichlet coefficients of the logarithmic derivative of the Rankin-Selberg L-function. So this is an analog of the von Mangold function, and sum up those coefficients up to x in residue classes mod q, as long as q doesn't exceed log x to the a, and we have the main term plus the error term just as in Siegel-Wolfish theorem. So that's nice. We have an analog of that. Our second application concerns symmetric power L functions, and it is based on cases of functoriality established by Gelbart, Jacquet, Kim, Shahidi, and Kim. Again, to simplify matters, I just state a special case. So let pi be a Caspidel representation of GL2, and let n be an exponent that we allow to go all the way up to 8. Now, Kim and Shahidi proved that LS pi times symmetric power and twisted by chi is meromorphic, and let's assume that it has no pole in the half plane, real part S at least one. So typically that's the case. Pi has to be very special, like dihedral, tetrahedral, etc., in order for this not to happen. So let's assume pi is typical just for the sake of simplicity here. Then there exists an ineffective constant C8 such that for all GL1 twists, this twisted nth-symmetric power L function that's not known to be automorphic because n can go all the way up to 8, not just 4, admits this lower bound and upper bound. Even the upper bound requires our lower bound because the idea is an idea already present in Kim Shahidi's work that when n is beyond the range where we know automorphicity, at least we can use the Clebsch-Gordon relations to express the twisted symmetric power L function for n as large as 8 as ratios of twisted Rankin-Selberg L-functions. And because we have in this fraction, we have good bounds for the numerator and the denominator, we have good bounds for the fraction as well. Anyways, it's time to tell you about the proof of our theorem. So once again, we would like to generalize Siegel's theorem in this full generality, all GL1 twists of all Rankin-Selberg L-functions. So how do we do that? So by the convexity bound for the derivative of the twisted Rankin-Selberg L-function, it suffices to prove a special case of the result, namely the one at sigma equals 1. It suffices to show, and that was Siegel's focus actually. Siegel was more interested in the value at 1 than other values because so his goal, I think, was not to prove the Siegel-Wolff theorem, but to bound the class number. So he focused on the value at 1. And here, it's just as in that case, it suffices to prove for the full force of our theorem the result at sigma equals 1. That is to say, L1 pi cross rho twisted by chi should be boundable from below by analytic conductor of chi to the minus epsilon with an ineffective constant depending on pi rho epsilon. And now I can tell you that we proved this bound in 3 steps. In each step, we proved the bound for a certain subgroup of characters containing the vertical shift characters. So in the beginning, as you will see, we start with the subgroup of vertical shift characters. So that corresponds to pairs of T and 1 as opposed to pairs of T and psi in the concrete description of chi's. And then we gradually increase this subgroup to finally reach all of F1, the full ideal class group. So in each step, we prove it for a certain subgroup, and we make sure that that subgroup contains the vertical shift characters. Now, in each step, we treat separately the characters chi for which the twisted L function might have a pole. That happens rarely, and that needs a separate treatment. So let me focus on the case when the guy has no pole. And here is the key thing. I try to make this carefully because this is very beautiful, and of course, this is the idea of Siegel. If all the twists for chi coming from the subgroup satisfy a quasi-Riemann hypothesis, meaning that the real parts of the zeros are bounded away from 1 by some positive epsilon, then we are done. A quasi-Riemann hypothesis, so a whole strip of free of zeros, gives you a much stronger lower bound than what we want to prove. So without loss of generality, we can assume that at least one of the twists coming from the subgroup violates the quasi-Riemann hypothesis, so it has a 0 very close to the 1 line. So we can assume that there exists an exceptional chi tilde in G such that the twist is entire. Remember that we only focus on entire twists now, and has a real 0 close to 1. Now you might ask, how can I assume a real 0 close to 1? Well, initially I only assumed the 0 with real part close to 1, but because my subgroup G contains all the vertical shift characters, no matter at which height this exceptional 0 might lie, close to the 1 line, I can just shift the L function so that this exceptional 0 happens to end up on the real axis. So because of this formalism of ideal class characters where the shifts by purely imagined numbers are included, I can as well assume that this chi tilde does the favor of producing Landau-Siegel 0 on the real axis where it should be close to 1. So without loss of generality, there is an exceptional twist, which is, although entire, has a real 0 very close to 1. Now we fix this exceptional, this mischievous guy chi tilde, and we can fix it as a function of pi, rho, g, and epsilon. Well, it shouldn't exist, but if it exists, I can think of it as depending only on pi, rho, g, and epsilon, not on chi, not at all. So each chi tilde just depends on this data. And at this point, we rename rho twisted by chi tilde. Note that we fixed chi tilde in terms of the initial data. We rename it to rho. And now suddenly the assumption becomes that LS pi rho, the original Rankin-Selberg that we are twisting on the way, is entire and has a real 0 close to 1. And this assumption, as it turns out, is quite powerful. Of course, this is Siegel's idea in action, but the way it works out in 3 steps in this setting is quite nice. Now, the 3 subgroups G corresponding to the 3 steps that I promised are as follows. The first, the smallest subgroup, is the subgroup of vertical shifts. That's step 1. In step 2, we add to the vertical shifts the quadratic characters. So we allow ourselves to shift the L function and also twist by quadratic characters. And in step 3, we want the whole thing. We want to look at all unitary. We want the lower bound for all unitary Hecke characters, not just special ones. Now, in each of these 3 steps, we apply the following key proposition. Let's look at the proposition. Let's fix our data as before. So pi, rho are the cuspidal representations of GLN and GLM over Q respectively, and chi is an ideal class character. Let epsilon be some small number, and let's assume that there is a beta. This will be exceptional real 0 close to 1. So in between 1 minus epsilon over 8 and 1. And now let's assume that the following 3 twists, the untwisted Rankin-Selberg, the chi-twisted Rankin-Selberg, and the chi-square twisted Rankin-Selberg are all entire, no pole for them. And let's also assume that this beta, which is close to 1, happens to be a 0 of the original Rankin-Selberg. Then we can lower bound the chi-twisted L function at 1 in terms of, well, the analytic conductor, and the exponent has this epsilon. So if the original Rankin-Selberg has a 0 close to 1, that hypothetical Landau-Siegel 0 can be used to lower bound the value at 1 of the twisted guy, and that's exactly what we want to achieve. Now, note that we have already assumed that the original Rankin-Selberg is entire and has a 0 very close to 1. So this assumption, and that the first guy is entire, is just given by the setup. And all we need to worry about is whether the other 2 L functions are entire so that the key proposition is applicable. And now I can go through very quickly how we can check these remaining 2 assumptions, the middle guy and the right-hand side guy being entire. This is necessary to apply the key proposition and achieve the condition. So in the first step, when we only deal with with vertical shift, so chi is a vertical shift. If this guy is not entire, then essentially rho is the dual, so up to a shift, which only depends on rho and pi. Rho is the dual of pi, and then the whole lower bound follows in a stronger form from the already mentioned work of Humphreys and Thorner, which recently appeared in Compositio. So in step 1, because of the work of Humphreys Thorner, we can assume that this guy is entire, but then all 3 guys are entire because they are just shifts of each other in step 1. So in step 1, we get the remaining conditions by the work of Humphreys Thorner. Now it's interesting how we get rid of the pole situation in step 2. So let's look at step 2. So we want to we worry about this middle guy having a pole. Now it turns out that if this guy has a pole, it turns out that's a separate lemma that chi falls into finitely many cosets of the previous subgroup. So the exceptional case for step 2 is when chi falls into finitely many cosets of the previous subgroup. But the previous subgroup already has been treated So for each of these concrete cosets, we have a free ride by the previous case, and that's how we eliminate the exceptional chi's in step 2. But of course, we need to worry about the pose of the second guy, but now the first two L functions are entire by assumption. And because in step 2, we are entertaining quadratic characters, only the third guy, the chi-square twisted guy, is actually a shift of the first guy. And because the first guy is already assumed to be entire in the previous initial, I mean, the Siegel type assumption, we have that the third guy is entire as well. So this is how we deal with it, the poles in step 2, and then the key proposition can be applied. And how about step 3? Well, in step 3, we have to worry about poles coming from the middle guy and poles coming from the right-hand side guy, chi-twist and chi-square twist. Now, chi-twist, possible pole of chi-twist can be dealt with as in the previous case, namely it can be reduced to the first step. Now, how about the chi-square twist? So it happens, so that's a slightly nastier case to look at, but now we have the result from step 2. So if chi squared introduces a pole in the Rankin-Selberg L-function by twisting, then it turns out that chi, not chi squared, chi lies in finitely many cosets of the previous subgroup, it turns out. So again, we have reduced the pole situation of the case to the already treated case of the previous subgroup. So that's how it works out. It's quite magical. Anyways, I want to say a few words about what makes the key proposition work. So as with the proof of Delavallee-Poussin and Siegel, behind everything, there is an auxiliary L function, in particular non-negativity. So the proof of the key proposition utilizes an auxiliary L function, which is given as a Selberg-Rankin-Selberg product of a certain isobaric sum. And when this actually has non-negative Dirichlet coefficients by a theorem of Hofstein-Ramakrishnan. And it turns out that you can factor this out just because pi is a sum of 4 guys. Pi tilde is also a sum of 4 guys. So when you match each term with each term, you will get 16 L functions whose product is ds. And here you see the 16. There are 8 in the first line, 4 in the second line, 4 in the third line. And the coloring is made so that from the green factors, we never get a pole. Why? Because in the key proposition, we are assuming that whenever pi occurs together with rho, if for trivial twist, chi-twist, or chi-square twist, those that occur in this product, those guys are entire by assumption. So the green factors, half of the factors is entire, no worry about the pole. So the poles can only come from the blue factors. In the first line, actually, S equals 1 is a quadruple pole because it's 2 plus 2 is 4. But there are potential poles coming from the blue factors in the second line and the third guy. Those poles might have multiplicity 2 or 1. Anyways, the poles are somewhat of a headache, but they can be controlled. So we know exactly where the distinct poles might lie. There can be at most 3 poles with various multiplicities. But what's important, what's crucial for the key proposition is that whenever S0, so it may be one of these 3 possible values coming from first line, second line, or third line. Whenever S0 is a pole of this product of some multiplicity K, it turns out you can just track that there are always K factors, same number of factors as the multiplicity of pole, whose size at the very pole equals the value that we want to estimate. So that's the key feature, and you can look into the details in our paper. I have definitely no time to explain it. Don't even intend it. Just try to show you what makes it work. This auxiliary function. And now here comes the amazing thing. Something that we realized after we finished the proof, not before. Let us look at this auxiliary function again. So this like horrible or complicated product. It turns out that in the special case, when pi and rho are the trivial representation, this becomes exactly the auxiliary function used in the Delavallee-Poussin proof. This product is very familiar to us from our first course in analytic number theory. And in the special case, when pi is rho and rho is psi, this product boils down to the 4th power of exactly the auxiliary function used by Siegel. So special cases of this auxiliary function are the ones used in Delavallee-Poussin and Siegel's paper. That's amazing. So our auxiliary function generalizes the classical auxiliary L function, and we only observe this in retrospect. And I really should finish, and I promised that I would finish with a surprise. I started with a surprise, and now I finish with a surprise. And here it is. So Jesse Thorner, co-author of this paper, visited me past week. And right now, he's on an airplane back to the United States. He visited me. And it seems that we can prove the following generalization of Tatuzawa's theorem over any fixed number field. So Tatuzawa's theorem is a strengthening of Siegel's theorem that not only we have, so one annoying or bothering fact of Siegel's theorem is that the constant is ineffective. But Tatuzawa discovered that with one exception, you can make the result effective. And here is a new result that I would like to announce so that you don't only get old stuff, but you get some new stuff. So I guess we finished proving this theorem last night in a restaurant. So this is announcement only, but I think it will check out. So you should take this with a grain of salt, but here's the result. I took all the effort to write it down correctly. So for every epsilon and n and m, so degrees of L function or automorphic forms, there exists an effective constant, C n m epsilon with the following property. Let's pick pi and rho from Fn and Fm. Then there exists an exceptional chi tilde, F1. So this is the one guy, such that for every other chi, either the chi twist is very close to the chi tilde twist. You see, you have to be very careful. I'm not talking about, so I cannot say that chi very close to chi tilde because these L functions might have self-twists. So you have to be very careful. So it's really the L function that shouldn't be close to the exceptional L function in the sense that it's not a shift by a parameter between minus epsilon and epsilon. If you are away in L function sense from the exceptional twisted L function, then we can claim non-vanishing in this region. And look at how beautiful that is. I hope it's correct. So it's C pi 0 C chi to the minus epsilon with a effective constant. But we only have non-vanishing. We don't have a lower bound. It's only non-vanishing. Anyways, I think that's the state of the art, and I had a good time on my birthday, best present I can have. I'm really grateful for the invitation. It was an honor, and I hope you had as much fun as I did.